Good morning to everyone who's joined us. My name is Scott Dahman. I am the Director of Business Development at PowerWorld Corporation, and we're really happy that you're here. Just a few logistical notes about the meeting. We are expecting quite a few people on the call, so please make sure you are muted unless you're speaking. And during Professor Overby's talk, we will ask you to add any questions to the chat window if you have questions, and we'll get to those at the end. And if there's time at the end of the presentation, and if there's an opportunity, then we may open it up to just some live discussion as well. But like the first avenue for submitting any questions will be through the chat window. The presentation's also being recorded, and we will try to download it and post it later to our YouTube as soon as it's finished processing and everything like that. So with that, I'd like to turn it over to our president, Mark Laufenberg, who will introduce Tom Overby. So Mark, please make sure you're unmuted and go ahead.
Thanks, Scott. I'd like to welcome everybody to this seminar by Professor Overby on visualization techniques and power system analysis. Just a quick introduction of Tom. Tom is a professor and holder of the O'Donnell Foundation Chair III in the Department of Electrical and Computer Engineering at Texas A&M University. Prior to joining Texas A&M University, he was a Fox Family Professor at the University of Illinois at Urbana-Champaign. He received his bachelor's, master's, and PhD degrees in electrical engineering from the University of Wisconsin at Madison. Most importantly for today's seminar, he is the original developer of PowerWorld Simulator and a co-founder of PowerWorld Corporation, and still very actively involved in the day-to-day operations of the company. He's the author of a widely used power system analysis and design textbook. We call it Gdv Overby Sarma here. He was also the recipient of a University of Wisconsin-Madison College of Engineering Distinguished Alumni Achievement Award and the IEEE Power and Energy Society Outstanding Power Engineering Educator Award, and is a member of the U.S. National Academy of Engineering. With that, Tom, it's yours.
Thanks, Mark, and thanks, Scott. As was said, I'm Tom Overby, and I'm going to talk about some of the new developments in PowerWorld Simulator for version 22, associated mostly with what we're calling the Gdv Summary Objects. The slides should be available. I think Scott sent an email out to everybody that has a direct link to the slides, so they're posted on the website. Also, in making up these slides, they created a number of different PowerWorld cases and displays, and those are also available for download. We put the slides separate just because some of the cases got pretty big, so even when they were compressed, they're like 400 megabytes total. Okay, so what I'm going to talk about today is mostly some of the new development PowerWorld's done in functionality called Geographic Dataviews, or Gdvs. The idea of Gdvs is to leverage information that's available with the power system, geographic information that is increasingly available, to kind of on the fly display that information. And then you can either just use the display on the fly, or you can save it and use it for future studies. I'm going to start out with a review of the Gdvs and then talk about some of the newer work that's gone on over the last year in terms of Gdv Summary Objects and Gdv Line Summary Objects. Actually, a lot of some of this was motivated by wanting to visualize very large system results. We were working on a project with SPP. I see Harvey is here from SPP, and we're looking at interconnection of the eastern and western grids in North America, and there was just a lot of information to show. So we wanted better ways to show it. In going through the presentation today, I'm using 4 synthetic electric grids to show the results. These range from 37 buses up to 82,000 buses. By synthetic, I mean they're fictional grids. They're all geographically based. They're actually geographically based in the US. Because they're fictional or synthetic, they don't contain any CEII, and hence they can be made fully public, and you can use these cases however you want for future work or in testing out what I'm showing here today. Okay, so one is a 37 bus case. This is one that we use a lot in undergrad education. That's a 37 bus one. The next one is a 500 bus grid that covers the northwest part of South Carolina. The reason why it covers the northwest part of South Carolina is the guy that built it, Adam Birchfield, is from that part of South Carolina, so he kind of did that area in his home state. The third one is a 7,000 bus grid that we've recently produced that covers the ERCOT portion of Texas. Again, this is an entirely synthetic, but it's a pretty good grid. And then the last one is the 82,000 bus grid that covers the continental US, I guess the contiguous lower 48 part of the US. In analyzing this grid today, I've actually got, it's divided into the three interconnects that we have in the US, the east, the west, and the ERCOT footprint. But in the results I'm presenting today, I've actually got the east and the west interconnected. So you'll see that in some of the results. Okay, and those are all available for download, and you can use them however you like. I think most people know that in the electric grid, when we show one lines, we use different colors to show different voltage levels. And here I'm using different colors to show the different voltage levels. For this 82,000 bus case, we deliberately designed it using voltage levels that did not match the voltage levels that were in the particular parts of the country. So we're using green for 765 kV. So we've got a WECC system that's served using 765 kV, 765 kV, and some of the SPP footprint. Again, this is a synthetic grid, so we did that deliberately. Here, our Texas grid is 500 kV, as is much of the Midwest. Okay. Gdvs arose about 13 years ago, and the reason why we created them is I was analyzing these grids, and at that time, PowerWorld already had geographic information embedded in the power flow. So we had buses mapped to substations, and we had geocoordinates on the substation. And I was thinking, can't we leverage this to show what we're looking at? And I'd be studying like the Eastern Interconnect, and I'd want to know where the different operating areas were. And I thought, I know where they are because I can just average the bus or substation locations. So how do I visualize that? The result was to create something called Geographic Dataviews that make it very simple to show geographic data. Now, the Gdvs were introduced about 13 years ago, but because most grids didn't have geographic information, then they didn't get as popular as I thought they would. But recently, they've gotten a lot more popular, partially because of the now widespread availability of geographic information in the actual grid. And also now we've got large-scale synthetic grids that have geographic information in them as well. The idea on a Gdv is you can show the information and then you can customize the information. The Gdvs can then be saved as a regular PWD file, or they can be saved as an aux file, which lets you edit them however you would like. So again, this slide just covers geography. Geography is much more a part of the electric grid than it was before. Some of this was because of the need to do geomagnetic disturbance analysis studies, but I think it's something that we really as an industry need to have in our data sets, since geographic information is such a part of everyday life now. So this first example, and again, I've got all these cases on the download. This first example is kind of what I'd call a classical Gdv display. It's based on the 82,000 bus grid, and in that 82,000 bus grid, every bus is mapped to a substation, and the substation has geographic information associated with it. And then we've got the system divided into operating areas. The operating areas here are mostly named for the states that they're associated with. And if I wanted to visualize that, what I could do is I could just go in and select the areas out of the Model Explorer and right click and do select GDV and create this image. Now in this image, what I did is the size of each rectangle is proportional to the generation in that area. Then it's colored based upon its exports, where I'm using a red-blue color mapping to show the exports. And I'll give you an example of this in just a second. Each one of those elements is then dynamically linked, so you can get easy access to its area dialog. And once it's created, it just becomes a regular one-line PWD file, so you can move the areas around if you want, and I'll show you that as well. In creating the GDV, there are a lot of customizations available, and we've got a dialog that we call the Geographic Dataview Style Options dialog. It allows you to specify how the GDV is going to appear on the screen. All of the GDVs are linked to a style. Now you can use multiple styles on one display, but often there's just one style. And then you customize the appearance at the style level. So here in the middle of the display in the white area, I've got total area. There I'm using a linear mapping between the field and the generator megawatt is the field here. And I'm saying if the value is 0, show it with a particular display size. And this is just a characteristic value that depends upon how big it appears on the screen. And then if it's got 30,000 megawatts of generation, show it with this amount. And then it just uses a piecewise linear mapping between the two. And we do fill color, line color, and things like that. Okay, so here's a second example. And this is for the Texas 7K grid. The image shows 4,900 substations, and it shows them without dynamic formatting. And then this is example GDV underscore example 2A. And then this one shows it with color mapping. In this case, it is set up by the substation generation primary fuel type. And this is GDV example 2B. Most of the presentation here today is just going to be slides, but I thought I would go through this one. Scott encouraged me to give a live demo of one, so I'm going to give you a live demo of how I created this display. So what I'm going to do is switch over to PowerWorld here. And this is the 7,000 bus synthetic grid. It's a 345 kV. That's the thicker lines there. And then the lower voltage is 13869 kV. If I do a case summary, I don't know if people can see that, but it's got 6,700 buses and it's got about 5,000 substations. So what I do is in Model Explorer, I just go aggregation, substations, and I get the traditional listing of the substations here. And I could scroll down, and in this case, there's almost all of them. Well, there are all of them, almost 5,000 of them. Of course, you could use the traditional standard filtering if you wanted to limit the number that appear. I then click in the field that I'm interested in, and you can show multiple fields. You just have to click in one to start. So I'm going to show the generator megawatt value. I right click there and I get Geographic Dataview. I can either Geographic Dataview the selected items, or usually I just select the column, then Geographic Dataview. So I do that, and it creates a dialog that is the Geographic Dataview customization dialog. When you create a Geographic Dataview, you need a map. And I have included in the download the most common map that I use, which is a North American map. If I'm showing Texas information, I just use a Texas map. So I'm going to browse to open an existing one line. I've got my Texas blank PWD there. So I click on that, and that opens up a blank display. And then I'm just going to click on the bottom button here, add geographic data view objects to the one line and close the dialog. And that will put all 5,000 elements on the dialog, each one, or on the one line. Each of these are linked. You know, so if I right click somewhere, I can look at the substation dialog for substation 4604. Okay. Now that's the basic display. Of course, because there's 5,000 of them, it looks like a mess. So let's go ahead and customize it. Once we've created it, I could save this as a regular PWD file, but what I'm going to do is customize it first. So I'm going to right click on some object and I select the bottom one here, which is View Geographic Data View Options. That shows the options dialog, which we were just at. Now I'm going to customize it. So what I do is I go to field attributes, and let's say I want to customize the total area. The total area is going to be size based on a field. And this field, there's a drop down. You can pick all sorts of different fields. By default, it's going to pick the field that we clicked on to start this process, which was the generator MW field. This is the mapping on the size value. You get metrics that says, hey, for this generator megawatt, the substation with the lowest value has 0. The substation with the maximum has 2,200 megawatts. How do you want to map them into a sizing? So I'm going to delete the middle point here. And this is where, having done this, you rapidly realize what are good values to use. I don't want to see the substations that have 0 generation, so I'm going to make their size, how big they appear on the display, 0. And then on this particular display, 100,000 works well. And if you're really interested in what that corresponds to, it's kind of the area of the how big the rectangle will appear if the generators, or the substation generation megawatts is 2,000 or 2,200 here. So then I make sure this field is clicked, which says, hey, use this dynamic sizing. And then I click OK. And now they're customized in size based on how much generation there is. The color is just some default coloring. So now I'm going to customize the color. I go here, View Geographic Data View Options. In the example, I showed the fuel type at the generator. So let me do that first. For fuel type at the generator, I just want to customize the fill color. I'm going to set the default fill color from blue to white. Although it won't matter too much here. And then I'm going to change the field here. These are all the standard PowerWorld fields. In particular here, I want to look at the generator type unit fuel, primary fuel type integer by megawatts, which just means the primary fuel type for the generators at the substation is going to be calculated based upon how much megawatts of generation there is there. That's a value. Oops, I want the generic one. This generic one. That's a value that goes between 1 and 16. What I did is I set up a color mapping that makes these generators look good. And then I just set it up as a available color map. It's the integer A16 color map. It goes from 1 to 16. So if I set 16 here, 1 there, and then I click OK, what you will see now is you'll see the generation colored by the fuel type. And arbitrarily, we said wind is green, and we said solar is yellow. We said natural gas is brown, nuclear is red, coal is black. Now, if I wanted to see the names, I'd probably go in here and lighten up the color mapping a little bit. So I might go back here and lighten it up so I can see the names. It's whether or not you want to see the names. Then you can see the type of unit at that substation and what the substation name says. And this could then be saved as a display, and you've got it, and it will dynamically update as the unit output changes, although of course the fuel type's not going to change. So let's say you want to view another field. So I'm going to go back, and now I want to change it. So say I want to know how's my reactive power loading at my generators. So I'm going to change the field here from a fill color of the unit type of fuel to its reactive power output. And we have a field now that shows a megavar percentage of the generator. The megavar percentage just says what percentage of reactive power is the generator producing relative to its limits. If all the generators are at their max var limits, it'll be 100%. If they're all at their negative var limits, it'll be minus 100%. So in this case, the range goes from minus 100% to 100%. I'm going to use a color mapping that is actually it's going to be a deadbend color mapping, such that I'm going to specify upper limit 100%, a breakpoint, let's say 50%, a negative breakpoint minus 50%, and then a bottom limit minus 100%. If I wanted, I could draw a color key here. Okay, and I've got it set to dynamically color them. And when I do that, it now shows me all of the generators, and I'm now color coding them based on their reactive power output. If the generators at the substation are producing between minus 50 and plus 50%, they're colored white. If it's negative vars, it's colored blue. If it's positive vars, it's colored red. So immediately you get a view of what's going on. Now you might look at that and say, well, yeah, but there's a lot of overlap there. And there is a lot of overlap, and I'm going to tell you how to get rid of that in just a second. But there is one quick way to get rid of it, and that is when we were looking at these displays, we thought, oh, a shortcoming of a Gdv is we're showing you the geographic location fine, but we're not making good use of total screen space. So we have an option. If you right click on a unit and view the geographic data view, we have something called Pseudogeographic Mosaic display, which we described in a paper like a year and a half ago. If you click on that, and I've got slides on this that I'll get to in just a second, and click apply or update Mosaic view, what it does is it dynamically resizes the display to make use of display space. So now I'm filling up, in essence, the entire one line here, and I'm showing the same information. It's just I've arranged it in columns pseudogeographically so that the ones in West Texas, like Odessa, are kind of towards the left. The ones in East Texas are kind of towards the right. But now I've used all the space. And if you want to see it that way, great. If you're like, I want to go back, then just right click again, and you click this button to restore it, and you can go back to the normal display. Okay. So let's say you want to do a larger display. Let me open up now the 82,000 bus case. And on this larger display, let's say we want to visualize all of the line loadings in the case. And this case has about 100 and some odd thousand different lines in it. Okay, so it's just taking a second to open up the one line here. Okay, so I'm not going to use this one line, so I'm going to close that one line. So I'll go network, lines, transformers. I've got 104,000 lines here. And let's say I'm interested in dynamically sizing these things by their MVA limit or percent of MVA limit. So I right click in there, I go down to Geographic Dataview, select column, then Geographic Dataview. Now I use my favorite one line, which is the North America blank one. I've colored the water light, so I call it the light one. And then I just click OK, and it puts all 104,000 elements on the display. It takes a second to do that, but there it is. That's all of them. And so it's all the lines. And of course, this is a total mess. You're not going to make sense of this. But each one of those is linked. So if I want to look at that particular line, it's some line in Western Missouri. Okay, but let's say we want to dynamically size these things now. So what I'll do is I'll right click on one of them to display the dialog. And then maybe I want to customize them by the size based on that field that I originally selected, which was the MVA percentage. And it goes between 0 and 167% of the MVA limit. The gist here is I don't want to see any that are lightly loaded. So let's say I say if it's between 0 and 85%, I set it as size 0. And then if it's a maximum 167%, again, I'll pick some value. Let me pick 100,000. I think that'll work. And I forgot to check to actually use that mapping. Okay, so now you see the smaller number of elements that are loaded at above 85%. And if I wanted to, I could go in here and say I wanted to show their actual value. So I've got the name shown there. The Gdvs can show up to 3 lines of text. So one of those lines is showing the name. I'm going to set the second line here to show the field value, which is just the MVA limit, which is what I selected initially. I'll show it with 1 decimal point there, and I'll add the percent. And now you can see all the percentages. Of course, how you size them, you could color them different ways. All of that is easily set up. If you just wanted to show them in a subset in a particular area, say Iowa, it would be easy to do. You just in the initial selection, just use the filtering to just pick the lines that you're interested in. Okay, so that's the only live demo I'm going to do here. So I'll exit out of this and go back to the slides. Okay, so I went through that example. That's 2B, showed you how to make that. Here's an example of the 80K system that's got about 40,000 substations in it. Here I'm using Gdvs to show the substations with the net power injection. This example 4 is one that is actually not a real power system, but we were using EIA 860 data, and EIA 860 data, of course, has all the generators in the US in it, and it's got the fuel types and all sorts of information associated with it. And we were trying to figure out a way to visualize it. And then we thought, hey, if we just use this and set up a dummy power system, we just kind of copied and pasted out of the EIA data and created a dummy power system, and then visualized it using a Gdv that I just showed you the approach here, where you're visualizing by substation the fuel type color, and the EIA 860 data uses the same fuel type codes as the PowerWorld uses, so it's very easy to visualize that. I've included that case. It's a fictional power system. What I did is I just I think I put all the generators at, I may have added dummy lines where they're all connected to one slack bus. It's not meant to be solved. It's just meant to visualize EIA 860 data. It didn't take long to do. It just took a couple minutes to create this. Here's one where we were working on a project. This one I didn't give you the data on, but we wanted to visualize some data. We had contingency analysis results, like SPP gave us something like 250,000 contingencies, and we wanted to visualize that. So I created a Gdv of the contingencies. Here's a Gdv showing remedial action schemes. The idea is if you have a contingency, say a remedial action scheme, and you look at the elements and the elements have geographic coordinates associated with them, you can map it to an approximate location on the screen. And of course, you know, it might not be perfectly correct, but you can move them around as you like. For contingencies, if it was a line contingency, we just put it at the center of the line. If it had 4 lines in it, we just average the centers and put them there. Of course, then they're dynamic. So when you run contingency analysis, you can dynamically size them based on the results. So it's very flexible. Okay, so creating the Gdvs, there's 2 ways to do it. I just went through the example of doing it in Model Explorer. You can also create them from an AXD file. When you create them from an AXD file, if you want to automatically set the location, you just set the SOX, the screen object X value, and the screen object Y value to 0, or else you can place them wherever you'd like, but usually you're just going to let the software determine the location. These next couple slides go through sort of similar something to I showed you, with the actual Texas case. This is creating one for switch shunts. So that Texas 7K case has switch shunts in them. There's 634 of them. So I went through and did the same procedure. I opened up the Model Explorer, looked at the shunts display, right-clicked and selected the Geographic Dataview, select column, then Geographic Dataview, went to the Dialog, again, picked a mapping file. I could have picked the Texas case map that I provided, or I could have picked the North American one, which is what I usually use. Then you select the style, and for style, there's a couple options. You can show them with rectangles or rounded rectangles or ovals or triangles. And then you can select the text to show. By default, it's going to show the name. You can pick the number, name number, or you can pick any field value you want. And there's up to 3 lines that can be shown. There's many different customizations. Here, I set the customization. So the fill color is based upon the bus voltage. I think I set the line thickness to be 4. And then I set the 4 pixels, and I set the line color, the border color, to be red if it's in service and green if it's out of service. And then the total area is set to the total megavars that it was having. And this is the display. So I'm showing the location, I'm showing the size, I'm showing its status, and I'm showing its bus voltage. So that's 4 attributes that are visualized here. There's 600 plus of them on the screen here. It's a lot of data to show, and you probably wouldn't show this much data, but you could if you wanted to. At a glance, you can see that there's only a couple that are open. Actually, when I loaded this case initially, all the switch shunts were in service. And I thought I should open a few up, so I opened a few up. So you can easily see the ones that have the green border there. There's a zoom view. You can as I showed you, go in and modify the style, modify the size. If you want to move them around manually, you can move them around manually to avoid the overlap, but I'm going to show you a better way to do that on the next slide. Okay, so an obvious problem with trying to show lots of GDVs on a display is overlap. There's 4 ways to address this. One is to manually move them, and that was the initial approach that we have, and that works if there's not too many of them. For example, on that area display that I started with, I would manually move stuff around commonly with that. There's a Pseudogeographic Mosaic display, which I showed you already. There's a force-based layout that we're going to get to, and there's Gdv Summary Objects. The Pseudogeographic Mosaic displays, we wrote up a paper on that. Jamie Weber was one of the authors of that. That was presented at the North American Power Symposium in 2019. The gist is with this, as I showed you, is we're just trying to dynamically move them around and resize them to use the full display space. And here's an example as it's transitioning. It can transition from 0% as the initial display, 100% is if it fills up the entire display. We do have the ability to make GIF files that kind of show this transitioning process. What I found is when I show those where they're kind of oscillating in and out, it gets sort of sickening. So usually we don't show those. Usually if I have a GIF, it'll just go from the initial and then it'll transition out and then you stay there. When you're using it, online, when you're working with it in the program, you can transition forward and backward, and you don't have to have it animate between them. If you just want to go from 0 to 100%, that's easy to do. But again, each one of these is dynamically linked. We've used them to show thousands of values. Obviously you're trading off display space. You only have so much space on the display, but as long as you got a couple hundred, maybe a couple thousand, they work out pretty well. Okay, the second way to lay them out is to use a force-based layout. The idea of a force-based layout is you model your elements in the code as having attractive forces and repelling forces. Basically, the objects are attracted to their initial point and they repel from each other. And the common way to do this is to use a Coulomb force. With a Coulomb force, it falls off with the square of the distance 2 objects are apart. So if they're close together, they push each other apart. But if they're far away, they don't tend to push much. We've got a number of different options to do this. You just go to the Geographic Dataview style options, and there's a page called Auto Layout. The Auto Layout gives a number of different options for laying out the elements. We've tried to set the default values here, like the relative attraction force, the relative starting point stickage force, the relative expulsion force, change per iteration. We've tried to set reasonable values there. I would just say to play around with this. We did set it up so you can do a layout, and if you don't like the layout, you can easily go back to the original values. So that's something that I commonly do. This is an example of the switch shunts where we're pushing them apart using this layout algorithm. It runs pretty fast as long as you only have, say, several thousand elements. As you start getting tens of thousands of elements, it can slow down some, but it's still reasonable to do. So I would just say play around with it. If you don't like a layout, you can easily restore back to the base values. In doing this, I will say one of the things we realized is we probably should do some boundary enforcement, because here, if you look at some of our switch shunts, if you're showing a map, these folks down here at the bottom got pushed out into the Gulf of Mexico. Maybe you don't like that. Some of them got pushed up into Oklahoma, so maybe we want to keep them in state. So what we did is we added forbidden regions. The way the forbidden regions work is if you check this box, you get to select up to 2 colors, and it will prevent your GDV from moving to a background location with that color. So it's very easy to keep them out of the water, because if your water's colored blue, and of course you can change it to whatever your water color is, you can keep them out of the water. You can keep them from going across the boundaries by setting the second color to the boundary color. The only problem is sometimes if your boundaries are too thin, they can jump over a boundary. So usually what you want to do is set your boundaries a little thicker in doing this. But it works pretty well. And of course, once you've laid them out, you can go into the GDV or into the display and just move the ones that have gone across the boundary back manually. This is an example of the layout algorithm with the boundaries enforced. Now what it did is it kind of pushed the switch shunts right down to the shoreline, but not out into the water. Of course, you only have so much display space here, so there's a trade-off. But this works pretty well if you want to get a pseudo approximate location, pretty close to the actual, but not having any overlap. Okay, and then there's options. You can fix some if you want some to stay fixed, then they kind of act as fixed points, and you can kind of move the other ones around those. That's an example with the fuel types that I went through before, just kind of showing the fuel types with the layout algorithm. Okay, so that's the basic GDVs. The next part of this talk is going to talk about the group display objects, which is something that we found very useful to summarize how the power system information. So in the early development of PowerWorld, when we first started doing this in, I guess, 94, we made a decision early on to separate the PWB files from the PWD files, separate the power system from its one-line representation. Now, that might seem obvious now, but at the time, PowerWorld cases were strictly defined graphically, so it wasn't clear this was the best way to go. But once we made that decision, then it did help drive a lot of subsequent PowerWorld developments. Within a power system itself, there are different ways to group objects. And these are ones that y'all are familiar with. There's substations, areas, zones, super areas, owners, things like that. And those are associated with the case. They're stored in the PWB. They're an attribute of the power system. The next slides talk about something that is an attribute of a display, and that is Gdv Summary Objects, or GSOs, or Gdv Line Summary Objects, or GLSOs. They provide a way to do the same grouping, or a flexible grouping, but at the display level as opposed to the power system level. So the advantage of this is that you can take a lot of data and dynamically group them, store them in a PWD, and then set up other groupings. So a single case can have all sorts of different groupings of the elements, and then those same groupings, since they're PWD display files, they can be used with other cases as well. So then the question is to say, well, okay, how do I group the elements? We set it up so that there's support for the AXD files, so you can customize how you like to group them. What I'm going to show you here is an easy grouping that we use quite a bit, which is to group them geographically based on an XY grid. Some people like this and some people don't like it because it doesn't enforce area and zones and stuff like that. But if you want to enforce that, you can just use the bus view and filters to only show particular portions of the grid and then do it geographically. So we try to be very flexible in this. The idea is when you set up a set of elements to be Gdv'd, like substations or buses or lines, when this Gdv customization dialog is called up, in the middle, there's a new option, which is Gdv Summary Objects. By default, it will use individual object Gdvs, and that's what I've been showing you all along, and that's the traditional functionality. Now, if you click this option here, Summary Objects by latitude and longitude, it will dynamically group your Gdvs into a latitude and longitude grid, and I'll show you that in just a second. You can also group them based upon a custom int1 field. So if you want to set the custom int1, if you set that to, it's an integer field. If you set it to different integer values, it will group them based upon that value. So that gives you a lot of customization in how you do this. Now, when you group in a set of objects, if you're using a latitude and longitude grid, you do have an option as to whether you want to put it at the grid cell, the location of the grid cell, or if you want it to be at the object average for the objects in that cell. A particular Gdv grid cell or grid area is going to have objects in it. Either you put the Gdv summary object in the center of the grid, or you put it on an average. And I'll show you the difference in just a second. The other thing you have to say is if you're going to be averaging fields, or if you're going to be grouping objects and you want to show information about those objects, how should I summarize the attribute? And that's specified by the default data type, the default summary object data type. The default is to sum up all the values. And if I'm grouping objects and I want to know how much generation is in this group, it makes natural sense to sum them up. However, if I want to group objects and show their voltage, it would not make sense to add up their voltages. Rather, it would make sense to take the average. So you've got an option to take the average. Maybe you want to look at the minimum of the elements in the group. Maybe you want to look at the maximum. So that's provided as a default, and then you can override it. Okay, so each GSO will summarize all the objects in its group. The display attributes are selected for the as for regular Gdvs, with the key difference that you have to select how the field value is calculated for the Gdv, which is down here. You can pick the style default, which is saying I'm going to add them all up. And as I said, the values include the sum, absolute sum, average, min, max. So here's an example of our Texas 7,000 bus case. What I did is I set up a 10 by 10 grid. And this was simple to set up. It's as fast as setting up a regular Gdv, except now this is for substations. Rather than showing all the substations, I dynamically group the substations into a 10 by 10 grid, and then I show a Gdv at the grid center. Okay, now what I've got this one set up as is I think the size is proportional to the generation, and then I set the color based upon the minimum voltages of all the buses in that grid point. Because I'm using the grid center, some of them appear off in the Gulf of Mexico. If you don't like that, you can just set them up to be based on the geographic center of the elements in the cell. And of course, none of our buses are actually in the Gulf of Mexico. So when I do this, it's the same 10 by 10 grid, but rather than showing them at the center of the grid, I'm showing them at the average for all the objects in the grid. Oftentimes that's pretty close to the center, but you can see it's no longer clear that this is a 10 by 10 grid. But I did get rid of the objects in the water. Maybe you like that, maybe you don't. So do you like this or do you like that? It's a simple option. And once you've grouped them, you can easily change them as well. What I did here is I went in and I right-clicked on an object. I opened up the Gdv summary dialog, and I grouped them using a 15 by 15 grid instead. Okay, and let me see if I can show you that. Okay, so here's the one I was just showing you, and this one has them in the Gulf of Mexico. I right-click here, and I go into this Gdv Summary Object options. Once you've created the Gdv, you can't change whether it's individual or summary. That's disabled. But you can change your grid size, and you can change whether you want the object average or the grid cell. So let me do that one first, and I update the display, and immediately you get that. If I want a 15 by 15 grid, I change it to 15 by 15. I update the Gdv summary objects, and I get a 15 by 15 grid. And this is a PWD, and you can save it. So if you wanted to get, I should be careful with doing this on the fly, but let's say I decided to do a 50 by 50. So there, now I'm showing a 50 by 50 grid, which kind of gets back to looking like the original display. So it's very easy to dynamically change this stuff around. Okay, so back to the slides here. Each one of those objects has a dialog associated with it. If you just right click on the object, you'll see a dialog. In the dialog, you can then see all the substations in that GSO, and all the substations are linked, so you can easily go to the substation dialog. So it's very flexible to see what's in your summary object. This I covered the Gdv summary data types, how they're defined, summation, average. Summation is going to work for like generation and load. Average is going to work for things like bus voltage or LMP or something like that. Okay, and then it's very common that you'll have a style default for that summation. For example, in the one that I just showed you, the area is based on summing up the total generation. So that's a summation, that's the default. But then the fill color, I want to fill it and show the locations where there's low voltage in the case. So I use the minimum field value here. Okay, so here's an example stability application. We did a lot of associated with this study that we were doing for Southwest Power Pool. We did a lot of studies on an actual electric grid, 110,000 buses of the east-west combined. So we wanted to better summarize results during stability studies. The next slide shows an example of that. This is that same Texas grid, 7,000 bus grid with results from stability, what PowerWorld calls transient stability. Now what I'm doing is I'm using the Gdv summary object, or the GSO, to show the change in voltage in the area for each group of buses. And then I've got a background contour, which is actually a whole bunch of little Gdv substation objects that I use to contour the frequency. And I'll show you how to get to this in just a second. But before doing that, I have to give a quick aside. The quick aside is something that is new with PowerWorld version 22, and that is the ability to store power flow states during a stability run. In PowerWorld, we have long had the ability that if you're doing a stability study at transient stability, and you want to pause at a particular time, you can pause it, and then you can transfer the results over to the power flow, and you can visualize the results. in doing this, we go into the stability result, pick out some fields, and transfer them over into the PowerFlow. So we're just copying fields. What we added in version 22 is the ability to copy those fields into a stream and then save that stream. And then you can save all these states and play them back at a later time. So this provides the ability to store these time varying PowerFlow states at pretty much as often as you like, subject to memory constraints. And this supplements and to some extent replaces the transient stability contour toolbar. The way you do this in stability is just on the transient stability options. There's a general page that's long been there. There's a new field at the bottom of that that says store full PowerFlow state on update. Whenever the code is transferred over to the PowerFlow, and that's a field that you specify in terms of how many time steps or what number of time steps should you have for an interval for transferring it, it will store the PowerFlow state internally in memory, and then you can store it in a PWB file. One of the concerns with this is you can use up a lot of memory doing this. To give you a ballpark value, it takes about 70 bytes per bus per time point to store this information. So if you're running a 20,000 bus simulation for 30 seconds and you're storing the results at, say, PMU frequency of 20 times per second, I guess that's similar to PMU frequency, a 20th of a second, that takes about 840 megabytes of storage. So when you get a PWB, it's going to be 840 megabytes extra. Of course, you're not going to do this often. It depends on whether you want to do it or not, but it's available to do. It really helps a lot with visualization because once you do this, you've got the results that you're going to visualize stored, so you can then play them back very quickly, visualize them, look at your visualization. If it doesn't do what you need it to do, you can change stuff around and replay them. So the stored results are available at results from RAM PowerFlow states. You right click and select transfer state to PowerFlow, select show PowerFlow transfer control dialog to automatically transfer the states. This is an example where I was running a stability study and say I wanted to look at 3 seconds, a contour of the volt or the frequency, and then I also want to see the bus voltages in my different GSOs. Here's a graph of the full results in terms of this frequency, and there are the voltages there. I guess I could quickly load that up. Okay, so this is a 7,000 bus case. It's an example that I provided you. It's the biggest example, and it's the reason why the case download is kind of big. But if you go to the add-ons, transient stability, if you look at results from RAM, I've got a bunch of PowerFlow states saved here. This is its results from RAM, and then there's a newer tab over here called PowerFlow states. Each one of these is a stored state. So if I right click on 3 seconds and I do transfer state to PowerFlow, it will transfer the state over to the PowerFlow. And if I want to contour here, I can put the contour on. Contour dialog is here. And that's what I showed you. if you want to go to, say, 3.2 seconds, transfer to power flow state, and it transfers it over to the power flow state. Of course, this would be tedious to manually do, so we've got a show power flow control dialog, and this allows you to start and kind of do what we did on the contour toolbar, which is sequentially go through all these stored states, transferring them over there. There's options then to save the one line as a JPEG, and then you can make movies. Okay, so that's available in version 22. And you have an example of it here. Okay, so you can do this for the actual values. What I find with stability results is it can be very helpful to do it using a difference case. So I oftentimes, if I want to make a movie up or show the variation in something, and with stability, usually you're showing the variation in the voltage magnitude, you can do that as well. This slide here, I saved the initial power flow as with the difference flows, and then this is a visualization showing not the actual voltage at each GSO, but its deviation from the initial value, and you can then make up a movie doing this. Okay, here's an example of a Gdv summary display for the 82,000 bus case with 30 by 20 grid. This is very quick to make up. Here I'm contouring minimum voltage is shown using color and size. So it kind of gives you a feel for what the voltage variation across your system is. Here's one where I changed it. I'm using a coarser grid, a 15 by 10 grid, so it's very easy to change around. Okay, kind of in wrapping up here, and I did want to leave some time for questions, so hopefully we'll be done by 15 minutes after the hour. One of the challenges we've had is with visualizing flow information, and the Gdvs have worked well for bus-based values, generators, shunts, substations, areas, stuff like that. And you could show the line values as an object, but we weren't really doing a good job of showing the flows. So what we've done is added some new ways to show flow values. The Gdvs can be visualized using line segments. So you can take your regular Gdvs, if they're associated with transmission lines, and visualize them as a line segment and customize them. I don't think this will be used a lot. It's available, but it's not going to be used a lot. And this slide here just gives an example of it with the 37 bus case, where I've got Gdv objects here, and then I insert the lines, and here it's one Gdv per line, and then I dynamically color them based on their percentage flow, and I think I set the thickness based on flow or something like that. It's available, and there are some applications, but it's not the most common application. I think one that's going to be much more common is to use something called the Gdv line summary objects, or GSOs. The idea of a GSO is, or GLSO, is we can group the line flows to better show the overall what is going on with the system. And the way GSOs are set up is from an existing Gdv display, inserting the GLSOs is simple. You just go in that Gdv summary object options, and there's a tab, or it's not really a tab, it's just a box, Gdv line summary objects, and you just click update GLSOs, and it'll put in the GLSOs. And there's a number of options to customize them. So here's an example where I took that first Gdv example, which showed the areas with the Gdvs. So this is for the 82,000 bus system. And then I've shown my Gdvs area, and then I add the GLSOs, and I've got the GLSO is set up so that I'm showing a green flow area proportional to the megawatt flow on the line. And then I size it based upon how many megawatts is going on the line. This is using an approach that uses a planar visualization, which makes it a little bit cleaner to see what is going on. Okay, and I'll show you this in just a second. The GLS details, they're just display objects used to aggregate the line flows. There's two ways to do it. The traditional way, in which lines go directly between their end objects, and this can cause overlap, or a newer approach that utilizes the Delaney triangulation algorithm, so there's no overlap. We described this in a Kansas Power and Energy Conference paper in April that's available on my website if you want to know the details. PowerWorld supports both approaches. So let me just go ahead and show you that here. Okay, so I'm going to open up example 1. Yeah, it's 80,000 in most cases, so it takes a second to load up. Okay, so here's my Gdv. If I wanted, I could go into the edit mode and move stuff around, but I don't want to do that. Okay. What I'm going to do is I'm going to right click on one of the elements. And of course, now I'm going from the edit mode to the run mode. So it takes a second because it's a large case. What I'm going to do is I'm going to show the dialog here. I should have done that. I don't know why it's taken so long to go back to the run mode. Okay, but there we are. Okay, so I show the dialog. All I do is these are area objects, so they're not GLSOs, they're just individual Gdvs. I have set up some customizations already. So I'm just going to click update GLSOs. And what it does is it updates the GLSOs and it just inserts them for you. If you want to see the options are right here for customizing it. It's how do you show the arrows? Is it megawatt flow? Or there 2 arrows or 1 arrow? Here I'm just showing a 1 arrow. It's very similar to the arrows on a one-line diagram. Okay, but this is, like I said, available at a click of the button, and it's going through and it's aggregating all the lines and it's showing the lines that go between the areas and then summarizing the flow on there. If you right click on this, you can see all the lines that are part of that GLSO. Okay, now this is using a Delaney triangulation algorithm where if a line goes from Oklahoma to Tennessee, it's going to be mapped as going from Oklahoma to Arkansas to Tennessee. That's just part of the algorithm, and it's explained in that KPEC paper. If you don't like that, you can use a more traditional insertion, and you just change the option from insert planar GLSOs to not, and then you update the GLSOs. You shouldn't get an error in doing that, but in doing that, what happened is it inserted ones that overlap. Like right there, it overlaps. You know, there's an intersection that's between, because there's a line going from West Virginia to the Ohio Lake Erie area. do you want to show that directly, or do you want to show it using a Delaney triangulation approach? We give you both options to do that. Now, on this particular display, it doesn't make too much of a difference. But with the other approach, it's a little crisper. Like on the other approach, this line from New Mexico to Oklahoma, it's going to be mapped into this segment and that segment. And that's all explained in that KPEC paper. Which one you do is up to you. Okay. So going back to the slides here, there's an example that I just showed you using the non-planar approach, and you've got intersecting GLSOs. Whether you want to use that or not is up to you. I showed you the dialog there with all the different line flows, and each line is also linked to give access to its dialog. You can customize this however you want. We do add the ability on the arrow density, which is similar to the arrow density field that's used on the regular one lines. If you insert a negative value here, it'll round that, take the absolute value, and then show a specified number of arrows per segment. So here's an example on that 82,000 bus system where what I did is I put on a 15 by 10 grid for the country. And then I show in each grid element the voltage. I color it based on the voltage. And then I'm showing the megawatt flow here with the arrows. There's also the option to put fields on these arrows as well. Here I put the fields using a black background and a white font to indicate that it's a line field. It's showing the flow on each one of those GLSOs. And you've got customizations available on the GLSO dialog, line field symbols that customizes, you know, what field do you want to show text for? Right now you can show up to 2 lines. Do you want to show, say, the first flow, the megawatt, the second flow, or some custom field? Here I've got the fill color set to black. I've got the font color set to white, wherever I guess the font color is right there. How many digits do I want to show? You can also dynamically size these. On this last one, you can see the black boxes are dynamically sized. I just did that based on flow value so that the flows that are high you can easily see. Again, this is something that you can create within minutes, if not faster, for a display. Use it however you like. But I think it's pretty flexible functionality. Okay, as a final example, we've got for the 82,000 bus grid, we did do a bunch of dynamic simulations. This was motivated by the SPP project where we were simulating an actual east-west interconnection using the real west and the real east, but we also did it with this 82,000 bus synthetic grid. This is the stability results for a 30-second run where I did a generator loss in the west, and then I show all 82,000 bus voltages here. And this is a visualization that we created using Gdvs and GLSOs and GSOs. The Gdvs are substations in the background, and they're used to produce the contour. The GSOs are summarizing the change in generation in different locations in our interconnect. Here I'm showing how many megawatts are being made up. This is for a loss of generation in Arizona. And then I'm using GLSOs to show the flows there. Okay. Scott, you'll have to tell me if this works. I'm going to try showing you this movie. So I used I stored the power flow states and then I created a movie. It doesn't take long to create a movie. Whether I can show a movie using the internet connection here or not, I don't know, but let me give it the old college try. And I included this MP4 on the download as well. So I don't know if people can, it's not doing anything yet, but this is just showing the simulation, and I just took a bunch of the images and put them together and made this movie. Actually, during a stability run, you can change how often you want to store the images. So I set it up so that I store the images 20 times a second for the first 10 seconds, and then 10 times a second for the next 20 seconds. So it's pretty easy to set up these movies and to visualize results on even very large cases. Here, the contour is showing the voltage deviation across the case. And you can see that we've got some voltage problems in New Mexico and some voltage problems in Wyoming, recognizing, of course, this is a synthetic grid. Okay. Did that show? Thumbs up, Mark?
Yeah, so it looked pretty good, Tom.
Yeah, okay. Yeah, and if it didn't look good for you, it's included in the download. Final thoughts, they provide a quick and flexible way to supplement existing visualization techniques. They're available in version 22. I'd say play around with them. We'd love to get your feedback on what works for you, what doesn't work, any functionality improvements. That would be great. Just finishing off real quick, we are, and this is if somebody's interested in having their images tested, we are starting to do human factor testing here at Texas A&M. And during COVID, we got some eye tracker equipment. This shows one of our research engineers. He's wearing eye trackers. He's looking at an image, and we can keep track of where he's looking on that image. So we have been doing some experiments on this, and we're getting a lot of really interesting data with it that we're going to start using to do more assessment. We can assess any program. So if you're running a program, we can assess it. If you're doing static images, like you might want to say, hey, how do my engineers perform this task with this image? We can assess it. To give you an example, when I was writing up the KPEC paper and showing the GLSOs, I visualized the PTDFs for a power transfer from Maine to Washington State, recognizing that I've got my east-west and the synthetic grid interconnected. So the magenta lines show the PTDFs, the white boxes show the individual values. And as I was looking at this, I thought, there's a problem. Something's not right. And there was actually a software bug that I have since corrected. But if you look at this image, and I know people looking at it online are not going to have it in high resolution, but if you look at this image, can you find the location of the error? So I gave this to our research engineer, and we used the eye tracker on it. And this is the result of how he looked at the image in terms of the eye tracking, and the images in the background. Then the eye tracker software tosses this in terms of, tells us what percentage of his gaze was at that location. This is a heat map of where he was gazing on the image. I've actually got a movie that he provided me showing how he looked at this image. And this, let me just, this is, the oval is where he's looking at on the image. And here I gave him a task. I said, Ike, where's the error? And he's looking around to find the error on it. And you can kind of see where he's gazing around. And then he circles in on the error there, and the error is actually at the Texas-Louisiana border. They didn't add up, so you can see that he's kind of focusing in on where the error is. So we get this data, and it's kind of cool data to get. You can summarize it lots of ways. And when he showed me this results, I said to him, and he was just testing it. It wasn't a scientific experiment or anything. I said, you did not see that image for the first time. And he ended up confessing that no, he hadn't seen the image for the first time. Because when I look at that image, and look at his eye tracker results, he did not look at all at Iowa. And that's where there's a lot of PTDFs going through Iowa. There's a lot of PTDFs here. I'm like, there's no way you really studied this whole image. That was my take. And then he confessed that, yeah, he'd actually seen the location before and knew where to look. So, but with real images, we can do more formal testing on it. So, I guess that's it. All right. Yeah, so we're testing different ways and trying to come up with testing methodologies. And this is just a final example saying if you look at those images, this is using Gdvs with line summary objects. That's a traditional one line. Is one better than the other? And you have to say, well, what question are you asking? What how would you evaluate that? And that's what we're working on. So that's our setup here at A&M. A lot of PowerWorld software in there. We hope you all can come down and visit. Does anybody have any questions? Scott, you're moderating.
I am. So far, there's nothing in the chat. I did just place a comment in the chat saying that we hope that this will be the first of a few sessions that we host in the near future, just coming weeks and month or so. We're going to talk about some other things that might be new in Simulator 22 or things that are improved, or maybe just give some updates on some features that we haven't maybe talked about in a while. And we're also welcoming presentations from other customers as well. We'll host the meeting on Zoom, much as we are doing today, but we invite other presentations if you are interested in making one. And I know we've got a couple from the Northwest that have been sent to me, and I've just been kind of busy trying to set this meeting up, so I haven't gotten back to those yet, but I will take a look at those and just invite others to send them in if you wish. And my email address is in the chat window. There's a question of when will version 22 be available, and the answer is March of 2021. So it's actually been out for a little while. I remember that because I was on vacation for my son's spring break when the launch was made, so I missed out on all the fun work, but I checked in from a ski lift to make sure that everything was going well, and it was. So you do have to be a current maintenance and upgrade subscriber. That needs to be current in order to get the version. So if your maintenance is lapsed, that could be one reason why you didn't get it. Or perhaps you need to check maybe with your IT staff or whoever's the gatekeeper for installing software and ask them to provide it. And if you're missing information or whatever, then we can send it to you too. You can send an email message to Kelly Wagon here, Kelly, K-E-L-L-E-Y @powerworld.com, and ask if perhaps some emails got lost or something like that.
Yeah, like most software, PowerWorld does update versions on the fly and patch things up. Like there was an error that came up in the presentation today that didn't seem to affect much, but I'm wondering why that error occurred. So it'll probably get patched pretty quick. And some of this GLSO stuff is new. So what was released when Scott was on the ski lift has been updated since then.
Yeah, that's right. We do have kind of a continuous upgrade cycle. The only reason we have different versions is because some changes are such that they require changes in the file format. So if it's a change that can be fit into the existing file format, then you will get it as soon as you download the next patch, basically. If it's a change that has to be deferred to the next version because it adds to or does something with the file format, then those come out with the discrete version releases. So Tom, there is one question that came to me that says, is there an easy way to plot a path from one station to another in a messy map? And I'm assuming that means like maybe automatically routing the lines if rather than maybe putting a straight line between A and B, maybe routing the line around some clutter. I'm not sure if we're working on that or if that's available. I think generally
that's not available. That's a good idea, and it might be something that we should add. It helps a lot to have geographic coordinates in doing this stuff. We do have the path between buses. You can get a listing of that, but we don't show it graphically yet. But it's something that we could certainly do. I don't think it'd even be that hard to do. But yeah, that I kind of wonder that sometimes too.
It's certainly possible to manually add vertices or take vertices away from a line. Of course, that's not automatic. It requires your intervention. But if there's something that's not taking a straight line, I know we can do that with fixed lines that are on there. Does that work with the GLSO objects also, Tom?
I haven't done that.
Okay. Because I know we can move. You can create a geographic data view with, say, substations or areas, like most of what we've done, and then, as Tom mentioned earlier, you can kind of manually move some of them out of the way if they overlap, or you can use the different methods that we have to automatically reduce or eliminate overlap. And it might be possible to do with lines as well.
This right here, this is the shortest path between buses, and that's existed forever and a day. And you see this right here. So on the fly, I will go to Geographic Dataview, select column, and this is a bunch of lines. I have no idea if this is going to work. And I will pick open one line, my North America blank. That's the dark one. Maybe I'll have the dark one here. Okay, with GLSO or with the Gdvs, I can put a line segment in, and it shows the line segments, but they don't seem to be connected correctly. So there's the path. So it's like, yeah, we can do it, but there seems to be a little bug in doing it. So that would be how I would do it. And since this was brought up, we'll go ahead and add that. In fact, we'll put that in.
Is it possible right now, Tom, to manually manipulate those screen objects, or?
Well, I think you could probably manually manipulate them around. It's not picking up the right. Yeah, it looks like it should be there. Okay, that wasn't something I knew what we could do. We don't quite do it, but probably within the next patch you'll be able to do it. And of course, if you're showing line segments like this, usually you would get rid of the names. You do none there. Maybe I'd show them thicker. And then we'll set it up so that they join together.
Tom, those are you're visualizing buses as line segments. That's what's going on.
Oh, are those buses there?
Yeah, it's a list of the buses on the way.
Oh, okay.
I think there might be another tab that shows the lines.
Where is that? I just.
Yeah, you're just in the Model Explorer right now.
Yeah, I'm looking for shortest path.
Oh, it's under. Is it in there? I thought it was under Tools.
Did it?
Oh, yeah. We must have had a right click there a while ago. I'd forgotten about that. Okay, yeah, we don't actually have the lines. We're just listing the buses.
So we'll add the lines and then we'll visualize them.
Yeah.
That'll be simple to do. Good thing to have.
All right, there's
And-
another.
Oh, go ahead.
Okay, I was just moving on to the next question. If you've got a thought to finish on that one, Tom, why don't you
I'm
go ahead
done.
and do that?
Those are my thoughts.
Okay.
Thought
New
if we need-
question. New
Mhm.
question here, and I'm not sure if I fully understand it. I'll take a stab at it and then maybe open it up to others here at PowerWorld to help with it. But the question is there a simple way to visualize PMU, not in a full one-line view, but rather when a user zooms to a specific part? And I mean, the way I guess I would address that is to use a conditional zoom level with the object. So whatever object you have on to represent the PMU, maybe a bus object or a substation object where the PMU data is being represented on, then just have that object use a conditional zoom so that it only shows up at zoom levels greater than X%, maybe 5% or 10% or whatever makes sense. Does that kind of cover it, or are there other things, particular with PMU visualization, maybe that you've been working on, Tom, that you have ideas on that?
What is meant by PMU?
I'm assuming it means, if the question asker wants to unmute, maybe elaborate, that might be helpful. But I'm assuming it means some data that you've loaded into simulator that's read in, or maybe retriever perhaps, that's being read in from a PMU data stream.
Yeah, Jamie might be better to answer that than me. I don't know.
I'm wondering if they're asking about like little spark lines to show the trace of voltage at a particular bus, Tom.
Yeah, that would be another, not a whole talk, but I mean, I didn't talk about spark lines, but there is stuff that we can do there.
Yeah.
And for people that are still on, if you've got images that you would like us to consider testing and getting like eye tracker results, right now we're kind of experimenting with what we can do with it. And I think it's pretty exciting new technology. It's just coming up with the right sort of questions to ask associated with the image, and then find out how people actually search through images and be able to document that.
All right, at this time, I'm not seeing any other questions in the chat window. I guess, are there any, this will be the last call. Are there any other questions before we adjourn the meeting?
Can you hear me?
Yes.
Oh,
Yeah.
Okay. That question, I asked this question, Slava Maslenikov, ISO in England. My question for PMU is related. I need to periodically update PMU data on one line and say that is megawatt flow on the line, which is read from PMU data and entered to say branch megawatt flow through SIM outer. And I need to periodically show this picture, say I'm showing average value for the last, say, 10 seconds. And that picture is updated every 10 seconds. So, and then I need to show it on specific portion of one line, not in the full line. So I know how to do it on the full online view, but if it zoom in, is it possible or not?
Jamie, sounds like for you.
I think we should talk about this offline, Slava, because I still don't understand the question.
Okay, thank you.
Is that okay? Just email it. Email us.
Okay, well, thanks,
right,
everybody. Oh,
There's, all right, if we got time, Tom, there's one more question, and maybe this is one for Jamie too, or maybe Matt if he's on the line. Is it possible to plot Gdv for SIM data input? I'm assuming you'd have to be able to get the SIM case in, and I don't know that there's a direct way to do that. We would read it in maybe from a CSV format that was converted from SIM, but I mean, generally the data inputs would be whatever forms you can open in simulator, and then what else you can load from an auxiliary file or paste in from another source that is compatible.
Yeah, generally speaking, Scott, I think that if somebody has a SIM file, especially like a SIM XML file, we would love it if you would send that to us. We have done a lot of work here over the years, and particularly in the last year or so, in getting SIM files to read directly into PowerWorld Simulator. We haven't released anything on that yet because we just simply have not seen enough examples. Our experience with the SIM files we have seen is that the C part, the common information model, is a lie. It's not actually very common. There's a lot of differences between various different SIM XML formats. So we would like to get our hands on as many different SIM XML files as we can. So if you have any example SIM XML files and you say, gosh, I'd really like to read this into PowerWorld and I'd really like to visualize this data in PowerWorld, please send those to us, because that will get us further along towards being able to release something that can actually, read in SIM files.
Yeah, and if there's object types in PowerWorld that can be remotely related to geographic information, example is contingencies, remedial actions, stuff like that, we can create Gdvs for them. We've added the Gdv support for a lot of objects that it didn't have it in version 21, like contingencies and some things like injection groups and stuff like that. So we just need an object type and then ability to get some geographic information associated with it. And then we can set it up for Gdv. We do have to set up the different object types for Gdv, which is adding code to say, where do I get the geographic information from? But that's not hard to do.
All right, another question, is the Geographic Dataview accessible from Python scripts in SimAuto? And the answer to that, I guess, would be to the extent, I believe you can show the GUI now through SimAuto, and to the extent that you'd be able to manipulate AXD files through your scripts, then perhaps that would work. Are there other aspects to that someone wants to respond to?
Yeah, we have added the AXD support to it. If there's particular commands, I don't think there's any particular SimAuto commands associated with it. Not saying that SimAuto commands couldn't be added. We're hoping people will look at the Gdvs and say, wow, this is useful for this or for that. Certainly in making presentations and images and stuff like that, I think it's very useful. I use it a lot in doing analysis on large systems when I don't know a lot about the system. Even when I do know a lot about the system, it's very helpful in tracking down errors and stuff. But yeah, I haven't set that up in SimAuto, but we do have the AXD support.
And there's a question not really related to Gdv, but just more general with Python and SimAuto. Do we have example Python scripts? And I'd say yes, check our website. We've got a training section that's on Python, and we also have a knowledge base, and we also have example SimAuto files on our website as well.
And we have taught a short course called Automating PowerWorld Using SimAuto that hopefully we'll be offering again soonish.
Oh, I was just gonna. Okay, Mark put the link into the training. I'll put the link in to the example files also, which you could probably get to the same files from both links. Oops, hang on a second. I sent mine to a particular responder only. Let me try to switch that to everyone. There we go. So then, yeah, now there's two links in the chat that provide information about Python. All right, well, Tom, thank you for the excellent presentation today. And like I mentioned, we'll be in touch in the near future with some additional sessions, and we appreciate everyone that came to join us today.